Hello, my name is Heather White. I am a graduate student in the Biological and Agricultural Engineering Department at Kansas State University. My research focuses on modeling the influence of subsurface drainage systems on downstream flooding in the Midwest. To begin, subsurface drainage systems are common in agricultural regions in the Midwestern United States. Drainage systems remove excess water from the surface and soil profile of agricultural fields, which has allowed crop production in previously unsuitable locations. Figure 1 below depicts subsurface drainage in an agricultural field. Drainage lines are installed below the soil surface and converge at an outlet location. The outlet conveys drained water to ditches, stream systems, and other conveyance structures. With this, it is evident that drainage systems impact watershed hydrology and could potentially influence downstream flooding events. Due to this, the objectives of my research are to construct a soil and water assessment tool, or SWAT model, to simulate stream flow in my watershed of interest, Skunk Creek watershed. To calibrate and validate the SWAT model using SWAT Calibration and Uncertainty Program, or SWAT CUP, to ensure both fit and accuracy of the model, and to implement and analyze the effects of subsurface drainage systems on downstream flooding from the watershed. To begin this project, I downloaded several data sets and modified them in ArcGIS to represent Skunk Creek watershed. Such data sets included a 10-meter digital elevation model, the 2019 National Land Cover Dataset, Circo soil data, and gridded prism climatic data. I also downloaded observed streamflow data from a USGS streamflow gauge station at the outlet of Skunk Creek watershed. Figure 2 depicts the digital elevation model or topography of Skunk Creek watershed. The red flags show the weather stations, and the green circle shows the USGS streamflow gauge station. After model construction, literature-reviewed parameters were selected for daily streamflow calibration and validation in SWAT CUP. To evaluate the fit and accuracy of the SWAT model, Nash, Sutcliffe efficiency, percent bias, and RMSE observation standard deviation ratio were used. Figure 3 shows the model calibration and validation on a daily time step. From 2007 to 2018, model calibration occurred for approximately 80% of the total study period. From 2019 to 2021, model validation occurred for the other 20% of the study period. Figure 4 shows the same calibration and validation, but on a monthly time step. Statistically, model calibration and validation both achieved satisfactory streamflow monthly statistics according to Moriassi. For example, calibration achieved a Nash-Sutcliffe efficiency of 0.604, a percent bias of 14.2, and an RMSE standards deviation ratio of 0.143. Validation results were even better with a Nash-Sutcliffe efficiency of 0.797, a percent bias of 5.57, and an RMSE standards deviation ratio of 0.057. In conclusion, both calibration and validation statistics indicate that this SWAT model can be used to evaluate different subsurface drainage, management, or climatic scenarios. Therefore, in the future, I will model and simulate subsurface drainage in select agricultural lands of the watershed. Then I will analyze the downstream model output to determine whether subsurface drainage systems influence downstream flooding. Thank you for listening to my presentation.